Today are these class of binaries, of which there's a growing class that is of direct interest for LISA. And I'm going to really focus today on just those that contain two white dwarfs. So this is an image that was drawn by one of my former graduate students. I didn't realize he had this in all of his talks, and I thought he'd gotten it off the web. And I finally said, "Where did you get that?" And he said, "Well, this is what I do." So this is his artwork. So this gives you just to set the stage for what I'm going to talk about today. All the binaries I'm going to speak of are systems where there's typically a very low mass degenerate helium white dwarf that's transferring matter that's hitting the outer disk, creating what we call a splash point, from which there's a lot of observations. And then the angular momentum, the disk is basically there to moderate the angular momentum loss to get that material down onto the compact object, which in this case isn't really drawn. As I'll show you as we go through this talk, in some of these double white dwarf binaries, the white dwarf is so large that actually this stream directly hits the white dwarf. So I'll talk about those systems today. So I've been interested in these systems now for about 3 or 4 years, and the work's been done with different people, so it would be very clear. So Chris Lloyd did his PhD with me in Santa Barbara, is now a postdoc at Northwestern University. Heis Nellemans and I have been collaborating on many of these topics for the last 4 years. He's now on the faculty at Nijmegen. And Dean Townsley was a graduate student at Santa Barbara, is now a postdoc at Chicago. And so what I'm going to summarize for you today, I'm losing a little bit. That could be interesting. Our work that's been done in a series of papers. And also I'd encourage all of you, you've probably seen this. There's a very nice article that Heis wrote in Physics Today in the July 06 issue, where he makes a lot of these issues about connections to LISA pretty explicit. For this crowd, I'm actually not going to spend much time on what this does or doesn't say for LISA, because I think the astrophysics of these objects is probably more of what you need to hear, rather than sort of a pitch about what LISA can do or not do. OK, so let me start by making it clear what's special about 1 hour, other than it's the typical duration of a talk, and provide some sort of astrophysical background for you. So everything I'm going to be talking about today is a donor that is filling its Roche lobe, namely it's reached its tidal radius, transferring matter onto some companion star. And so we demand that basically the radius of that star, R2, equals the tidal radius, which is written here, where A is the separation of the binary, and M2 and M1 is a mass ratio. If you demand that the Roche lobe filling star, the star is Roche lobe filling, and then you just take the basically Kepler's law, omega squared is gm over a cubed, and write things out as the mean density for this donor star, which is then m over r cubed, you can get a relationship between the orbital period of a binary and the density of the Roche lobe filling star. Okay? So if you have a density of 1, and of course grams per cubic centimeters, those are the only units you should ever use. Okay? So 1 is water, and by the way, the sun. The sun's about 1, and so are you. You're about 1. Your orbital period is 10 hours. Okay? If I put in this as a donor star, a main sequence star roughly has its radius going like its mass. And so if I put that in for the mean density, I then get a relationship between the orbital period and the mass of a main sequence star, should it be filling the Roche lobe. Okay, so if I have a solar mass object, it's about a 9-hour orbit. If I'm doing mass transfer from that object, then the orbital period is shrinking as a function of time. Okay? And what happens is that you reach a period minimum. And so what's shown here is a little bit more details than we need. This is, yeah, I really am losing the left hand of my plots here. I'm going to forge ahead and just assume that I can tell you everything you're missing in the left quarter of an inch. This is mass accretion rate in the binary as a function of time, showing mass transfer rate 10 to the minus 8 to 10 to the minus 11 solar masses per year. If I start with an object with a period of 6 hours, then it's about a 0.6 solar mass star. And what happens is the mass transfer rate is dropping. I'm not going to go into those details here today. But basically, over time, this donor star is whittled down from 6 hours all the way down to about an hour. And then you see here there's a period minimum, and the star actually starts to expand. And so why is that? Why is it that a main sequence star, as a function of time, as I transfer mass from it, keep pulling material off, eventually it gets to an orbital period minimum, and then after which expands? Well, the reason for that was made quite clear about 25 years ago, which is eventually there gets to be a mass transfer rate such that as you pull matter off the star, it actually does not have time to find the new thermal equilibrium. There's a characteristic time scale for a star to find thermal equilibrium called the Kelvin-Helmholtz time. And if the mass transfer rate gets to, or let me say it correctly, if the mass transfer time scale gets to be shorter than the time for thermal readjustment, then the star expands under mass loss, because if you take, if it's just changing its mass adiabatically, the star expands. And so that picks a mass scale where those crossovers between the Kelvin-Helmholtz time and the mass transfer time occur, and that's about a tenth of a solar mass, after which the radius roughly just asymptotes to a constant. So you end up with an orbital period minimum of about an hour, and the donor mass at that point is about the mass of a brown dwarf. So if you have a hydrogen-rich system, a system that starts at the main sequence star that you're whittling down under mass loss, basically can't get below an hour. Okay? So that's the first thing to know. The second thing to know is that there is a very well-observed period minimum, and it's off of this by about 15 minutes. It's about 75 minutes instead of 60 minutes, and there's 100 papers on that topic. It's an interesting topic, but I think for this audience, I just wanted to make it clear that there is something about 60 minutes. So if somebody tells you you've got an orbital period shorter than that, then something's funny. So the class of systems that I'm going to talk about today are this class named after the prototype. So for those of you who know how to name variable stars, you can tell me in the Canis Venaticorum constellation which one this was. Nobody knows the scheme, but this is telling you the constellation it's in, and this is telling you that it's around probably the 10th or the 12th, something like that. There's a weird numbering scheme, lettering scheme. It's the prototype of the binary. So it was found by people actually here at Caltech. Humason and Zwicky found that as a faint blue star in 47. There's a spectrum, which I'll show in a minute, that was from Greenstein and Matthews, that it just showed helium lines. And I'll show you what that looks like. The later work found that this system had a 17-minute orbital period. So what's shown here are the names of all the systems to date, and the orbital periods, from 5.3 minutes all the way back out to 65 minutes. And there's 3 objects that were found with the Sloan Digital Sky Survey for which we don't actually have an orbital period yet. Okay? And the first thing to see is this is a, stars are named by variable star names, so these are typical variable star names. This was found by ROSAT. This was found by the Sloan Digital Sky Survey, as was this. This was found as a supernovae, but it wasn't a supernovae. It was misidentified. Hence, it has the name of a supernovae designation, but it's not. Okay? And you're starting to get a sense for this pretty heterogeneous class found in many different ways. But the expectation is that this list is just going to keep growing with time. And it really has exploded. So when we started on this work, none of the Sloan objects were known. These 2 weren't known, and the supernovae. So this sort of has doubled in a 5-year period. Okay. How do we understand these short orbits? Well, in this case, what's filling the Roche lobe is a helium white dwarf, as I'll show you. If you have a very low mass degenerate object, the radius of that object goes like 1 over m to the 1/3. And so that relation I showed before would tell us that that tells us the density goes like the mass squared. And then if I put that back into my orbital period mass relation, which I derived, that gives me the orbital period as a function of the mass of the donor. And you can see if it's a tenth of a solar mass helium white dwarf, it would have a 7-minute orbit. But it's a white dwarf, so as I pull mass off, the radius increases, the orbital period expands. And so this range implies donor masses of 0.006 to 0.12 solar masses. So this guy here has a 6 Jupiter mass object. Jupiter is 10 to the minus 3 of the mass of the sun. So this has a 6 Jupiter mass helium star. Okay, that's the companion. Okay, so far I'm okay losing my 1/4 inch, but I know it's going to get me. So let me show you a little bit about these systems. So what's quite dramatic is that we are really revealing the helium core of a star, and I'll explain how that happens. But the interesting thing is that that is what had been the interior of a more massive star, and it was doing hydrogen burning. So what we're seeing is the ashes of hydrogen burning from the main sequence. So here's the spectrum from 4,200 angstroms to 9,500 angstroms of one of these objects. Doesn't matter which one. What you see here are all the helium lines. These are all helium lines, this is the line where there would be hydrogen. Here's the Balmer series would be here. Here's H beta. Here's H gamma. You see there is nothing there. There is no hydrogen in these systems whatsoever. And that's what called attention to them, in addition to their orbital period, is that the complete lack of hydrogen. Okay? What's also interesting is that there is a very large amount of nitrogen, very little carbon. So nitrogen to carbon is bigger than 100. So here's nitrogen lines, which are very unusual. And there's also very little oxygen. Nitrogen to oxygen is 50 times the normal value. So these are relative to solar. So it's nitrogen enhanced. Now why is that? Well, when you're doing hydrogen burning on the main sequence, you're doing it via the CNO cycle, which is using the CNO as catalyst to burn hydrogen to helium. The slow step in that reaction network is proton capture onto nitrogen-14. So all of your catalysts are piled up at nitrogen-14, and the carbon and oxygen are basically gone. And so again, this is consistent. What you're seeing is the ashes of hydrogen burning, which is helium plus nitrogen-14. Okay. The other thing is I'll talk about today is here's 0. So you might notice there is a beautifully flat spectrum, featureless continuum here. Okay, which I'll talk about, or something we've explained, is basically this is the accreting white dwarf itself, which has been reheated, providing this light. And I'll show you how now that's really been shown to be. Well, we know that now. We didn't know it. We knew it, of course, as theorists. We didn't get the observers to believe this until they really observed it. And I'll show you that today. That something just came out. Okay, so that's what the spectrum looks like. So for those of you who do stellar spectroscopy, there's nobody in the room. Okay, this is weird. I mean, this is not your normal object. So here's Rob Hines, if you don't know, has a beautiful website where you can grab a piece of code called binary. It's Bildsten, and it allows you to create realizations of any binary you have. So this is his realization of one of these systems. So here's the companion. This is to scale, okay, showing where the splash point is again, which is going to come up in a minute. The accretion disk and the white dwarf's down here somewhere, and this is the object. So the question here is, how are they formed? How many are there? How do they evolve under mass transfer? So I'm going to try to today address as many of these issues as I can for you. So the first question is, how do you make these objects? And there's a beautiful paper by Heiss and his collaborators from 3 or 4 years ago. I'm just going to give you one scenario. In population synthesis, for those of you who've done it, you know that there's always many ways. Once you know the outcome, there's many paths to get there. So I'm just going to give you one path. So imagine a system which initially had some massive star, which has done its stellar evolution, has formed a 0.6 solar mass carbon oxygen white dwarf. That's what this is meant to represent. And this was, let's say, a 2 solar mass star or something. And then what's remaining is a lower mass star, 1.5 solar mass star, that starts to go up the red giant branch. And so when you're going up the red giant branch, you have a helium ball at the center, which is going to eventually ignite if the star is allowed to do what it wants. And that helium core is increasing in mass because the red giant's powered by hydrogen burning, and that's increasing the mass of the helium core. Okay? So this object's expanding in radius. If the binary is tight enough, then this object will start to overflow its Roche lobe. It'll fill the Roche lobe. Okay? And it'll start to try to transfer this envelope onto this object. But this is more massive than this object. And what happens in that mass transfer is that as it transfers mass, the Roche lobe actually gets smaller, okay, because you're making this object more massive. But the red giant's expanding. And so you basically get a dynamical runaway. You can't get a stable mass transfer. So then we sort of really do close our eyes and wave our hands a lot, okay, and say, in the end, here's what I have. Well, what happens? So the way you at least conserve energy in what's called a common envelope is you say, well, all of this matter, which is maybe as much as a solar mass or 1.2 solar masses, because of this dynamical instability, fills this binary. And then I have these two little cores which spiral in, right, dissipating orbital energy into the envelope, which goes to infinity. So I end up with a tight binary in the end. Okay? And we see these. We see double white dwarf binaries on the sky. And so this system, let's say, might end up with an orbital period at the end of a half a day. And then you have to wait for gravitational waves to drive it into contact. Okay?
How much mass is it on?
In this case, a lot. This is a solar mass envelope. That's actually what sets how tight these can get. So the best case scenario, well, the best case scenario is very inefficient, which is that you radiate a lot and don't eject much. So nobody can. So in the end, from this process, there is some distribution of orbital periods, which completely determines the amount of the population. And there's no way you can really sort of ab initio claim to understand what this orbital period distribution is. Okay. All right. So what happens once we start that mass transfer now? So now we have, in that case, I showed you, let's say, a 0.2 solar mass helium white dwarf, okay, and a 0.6 solar mass carbon oxygen white dwarf. So those objects in spiral, the low mass object is puffier. It will fill the Roche and start to transfer matter, helium, onto the carbon oxygen white dwarf. And that's what we think we see. The orbital period at that point is maybe a minute, something like that. Okay. What happens? How do we understand the mass transfer? How do we understand the evolution of that binary from there on? Okay. Well, we can just write down the total angular momentum in the orbit. I'm going to ignore spins. That's the angular momentum in the orbit for two bodies. I'm going to assume that the helium white dwarf fills the Roche lobe, and so its radius is basically given by the tidal radius. And so I'm just going to take the time derivatives of this equation to give me the angular momentum changes, the orbital period separation changes, and the mass transfer rate. And I'm going to assume that the radius of that donor has some power law dependence on n. This might be minus 1/3 if it's really a degenerate helium object. And that allows me then to get an equation between the angular momentum loss to infinity, which all of you know, and I'll show, is from gravitational wave emission, sets the mass transfer rate. This is the rate of mass transfer from one system to the other. Okay? And so for these systems, the mass transfer rate is indeed just gravitational waves, and this was really shown nicely when the first one was realized back by Faulkner, Flannery, and Werner. And then this allows you to just calculate a time evolution. This plot's not new. It's just from a paper we did recently, showing how the mass transfer rate changes from the beginning of onset of mass transfer at a very short orbital period. And then as a function of time, that mass transfer rate drops, as you can see, 6 orders of magnitude. And you get out, in a Hubble time, you roughly can get back out to almost an hour, or beyond an hour again. That's why I said that last one you might have seen was 65 minutes. You can get there in a Hubble time, okay? Or actually in a few gigayears. Okay, so there's a tremendous amount of richness in the phenomenology of what the observers see, given this large dynamic range of mass transfer rate. Almost none of this I'm going to tell you, because you'd really fall asleep. Yeah?
So if we understand this as, in the absence of gravitational radiation, the system would reach a stable orbit with no mass transfer for a given radius.
It would.
Due to the radiation, the orbit gets tighter, allowing the mass transfer to occur. That's how they're connected.
Yeah, so let's say after that common envelope, you have a half-day orbit, whatever the number is. If there's no gravitational waves, you're done. You just sit there forever. The gravitational waves are needed to drive you close enough that you can do mass transfer. And then once you're doing mass transfer, it tells you how that evolution proceeds. Yeah. So there are some systems when you have an active star where you don't actually need gravitational wave emission. You can be tight enough that you're tidally locked. But then if the star is losing mass in a wind, that gives you an angular momentum loss to infinity, which can sort of act the same. I mean, it's different physics, but it can sort of appear to be the same. Okay. And so as I said, in time, you can go back out to 60 minutes. So this is orbital period as a function of time. And you can see you can get out to 60 minutes. Here's 10 to the 9 years. Here's 10 gig years. Okay, so everything I've told you so far really is sort of theory, in the sense that the expectation is that these have very low mass donors. However, until basically last week, for the double white dwarfs, we actually had no proof. Okay, so I'm going to show you some of that today. However, there are some systems where you have everything's true that I told you, except I pull out the carbon-oxygen white dwarf and I put in a neutron star. We've known about those for about 5 years. That's what got me interested in the problem first. Some of those neutron stars are pulsars, and so you have a velocity. You get a very good velocity. In those cases, we really did learn, and I'll show a plot of that the donors are really these low-mass objects as expected. Okay. Looks like Kurt has a question. No. People should interrupt. Okay, so what we got interested in first was understanding what are the properties of these very low mass helium objects. So this is a plot from Zapolsky and Salpeter from after I was born, 1969, showing the mass of a star in log units. So you maybe can't see in the back. Here's 10 to the minus 2 solar masses. Here's 10 to the minus 3. And this is radius in about 0.0. This is not a log. This is just a linear scale. The radius of the object. Okay. So here's Jupiter. Here's Saturn. Here's Uranus. Here's Neptune. Okay. So we're sitting roughly around here at 10 to the minus 2. And here's the helium curve. Okay. So the point is, these objects are not just simple degenerate objects. The Coulomb physics, the physics of the fact that there's charged particles in there, which tend to attract, matters and sets the radius. So the first thing to see is that hydrogen or a cosmic composition objects are much puffier than a helium, carbon, magnesium, or iron object. And that's because of Coulomb physics. The Coulomb attraction makes these objects more tightly bound. Okay, and the other thing to realize is that all the theory had been done for t equals 0, which is a great theoretical problem, but nobody had ever done finite temperature. Okay? So I'm not going to work through all this, but let me just give you two limits that you know and love. So this is the limit at very high masses, where basically what's holding up the object is degeneracy pressure. Then the radius does go like mass to the minus 1/3. Okay? At the low mass end, you're in the limit that's this table or your piece of metal, which is where basically the Coulomb physics and the degeneracy pressure are exactly matched. That fixes a characteristic density. Okay? If you have a characteristic density, then the radius goes like mass to the 1/3. Okay, it's rock. So this is the rock limit that you know, and this is the degenerate limit. And we're, unfortunately, or fortunately, depending on whether you're looking for work, in the intermediate region. Okay? So part of what Chris did for his thesis, I did some of this initially, and then Chris did a lot of work really understanding what these objects look like when they have a finite temperature, because t equals 0 is probably not a good limit. Why do we think t equals 0 was not good? Well, this is a plot from an original paper I did. This is these X-ray binaries. So what's shown here, all we need to look at is this curve. So what's shown here is the radius of the donor star, in this case, this is 4/100ths of a solar radius. And this is the mass. So here's 1/100th and 0.02 solar masses. And so for this object that's filling the Roche lobe, we know there's a relation between the radius and the mass. That's shown by the dashed line, this dotted line, sorry. But because we actually know the binary has to be at least edge on, or inclination, this would be if it's edge on. And then if I incline it, because we don't know the inclination, we move up this curve. So the minimum solution is here, but here sits the cold helium. Here sits the cold carbon. They don't intersect. We can't get a cold object to fill the Roche lobe, which told us the objects had to be hot. Okay? And so the initial stuff tells us, this is roughly 10 to the 5 or 10 to the 6 Kelvin, that to fill the Roche lobe for these objects, it actually has to be hot. The other thing interesting for the neutron star case is you see this one has a lot of solution space where it cannot be helium. It has to be a carbon object. We don't see this in the white dwarfs, but we do see this in the neutron stars, where many of these objects are probably getting their material from a carbon-oxygen white dwarf. But that's not really what I'm going to focus on today. So we had evidence, direct evidence they were hot. Okay. Well, how hot should they be? What do we expect? Well, so we have this common envelope event that basically just took that helium white dwarf and suddenly exposed it. Okay, that event that led to that ejection of the envelope exposed it. And helium white dwarfs actually cool pretty slowly. Okay. So if you, after that event, then think that in, say, a gigayear, it will merge, you can just ask, what will the temperature be after a gigayear of white dwarf cooling? Then the core would be 10 million Kelvin, so 10 to the 7 Kelvin. Okay. However, by the time we see it, it's had a lot of opportunity for mass loss and expansion. So it's actually adiabatically expanded, and so therefore it's going to be colder. Okay. And for a Coulomb liquid, I'm sure all of you know the result, that it's a different scaling. Okay. You get a very different scaling. The entropy is in the ions in this case. But roughly speaking, this would tell you that if I started with a 0.2 at 10 to the 7, that this was really for the neutron star problem, it doesn't matter, that we expect, you actually, if you calculated it, you'd expect a core temperature that's around 6 by 10 to the 5. Okay, so it's sort of in retrospect, we should have predicted this. I mean, we didn't, but this is what you'd expect from that scenario. So what's interesting, it starts to tell us that scenario is maybe not crazy. Okay. So what's shown here now are sort of more sophisticated models of, again, this is radius in log units. This is mass in log units, okay, of the star. So these solid lines are helium white dwarfs with different core temperatures, 10 to the 5.5, 10 to the 6, 6.5, 7, 7.5. Okay? And then shown on here is the old Sapolsky and salpeter relation, T equals 0. Okay? And then these lines are showing the orbital. If this is a Roche lobe filling object, then for all of the AM-CVM binaries, you can draw a line, which is the system has to live along this curve, because I know the orbital period, I know the mean density, and therefore I can draw a line, which is for a constant rho. Okay? So if you look at a system, you can immediately see what the impact is of a hot donor. So it's easy to sort of look here first. So if you look at this object, you can see that I can have a Roche lobe, I can have many different solutions, but this solution has a higher mass than this solution. So if the temperature's hot, I end up having a higher mass object as my donor for that orbital period. Okay? So if you actually think from the orbital period you can predict the gravitational wave signal, the answer is no. You don't know enough, okay? Because you have to actually know the temperature of the donor. Okay? And the sign of this is maybe positive for those trying to do this, which is it's a larger signal than you'd expect from just a degenerate object. Okay? However, that's the good news. The bad news is that you evolve faster through the bandpass, okay? Because everything's happening faster. Okay. So again, what I said is that sort of from the traditional scenarios, we expect roughly temperatures in this range. So it won't be surprising if we ever can get real data from these systems to find masses that are offset quite a bit from this line. Okay, so this is sort of trying to give you a sense of what this means for the gravitational wave signals. So this is a plot from the paper with Heiss. So this is just a typical 0.6 plus a 0.2 solar mass white dwarf at a kiloparsec. This is orbital, everything's cut off. This is orbital period in minutes, okay? And this is the log of h, this is gravitational wave string. So this is the object coming in. This is just how it evolves, if you could watch it. And then depending on what the radius is of this object, if it's really hot, it'll have a big radius. It'll fill the Roche lobe at 10 minutes and then move back out. Okay? This time here is 10 million years from when you reach contact. If it's colder, then it goes in further, okay? Because the object's smaller, fills the Roche lobe later, and then comes back out. But you can see here at a given orbital period, there's a large dynamic range of possibilities. Right? Here's a factor of 3 in the strain. Okay.
What 3 temperatures are you plotting?
This one was actually pretty extreme. This was actually, I think, higher than 10 to the 7 at contact. So the variable here, so let me tell you, what's the variable here? The variable here is the merger time. So from the common envelope, right, the question is how much time do you have to cool before the merger? So if the common envelope is very efficient and brings them all in close and they merge in a million years, then all the white dwarfs are hot initially. Okay. If instead it's an event where after the common envelope it took a long time to merge, right, then you'd be more on this track. So this is a probe. So if you ask what's the temperature telling you, it's telling you that merger, just the distribution of merger times. I mean, if you had a great data set, you could start to unravel that.
The bottom curve is basically a Hubble time to evaporate the common envelope.
No, sorry. I have the common envelope, which that's instantaneous on a cosmic time. After the common envelope, I have a helium and a carbon-oxygen white dwarf. But their orbital period after the common envelope sets the time scale for the merger, or for the coming into contact. Okay.
So for typical parameters, what's the fraction of the pressure that's coming from thermal effects?
It gets to be much bigger down here, so it depends on what the mass of the white dwarf is. So at early times, it's very small. Mm-hmm. Okay, but because basically because the entropies in the ions and the initial pressures in the electrons, they don't sort of scale at constant entropy. You don't get a simple scaling. So down here, it could be 10 or 15%. Right? Yeah. Okay. So let me talk about this object this was just on AstroPH 2 nights ago. I got the data just last week from Tom Marsh. So there was an object found in the Sloan Digital Sky Survey with a 28.3-minute orbit that was eclipsing. So for all of you who do stars, if you got an eclipse, you're golden, right? You can do a lot. So they went out with an instrument that Tom Marsh built called Ultracam, which simultaneously takes multiple colors with about a 1 second resolution, time resolution. Okay? And so this is showing the time series. This is from WHT, which is the Herschel telescope. I think this is about a 4-meter telescope. It's a 19th magnitude star. Okay? So it's not that faint. And so here are the eclipses. Now there's a lot of things you might notice about this. First off, he's got a really nice sampling because all the eclipses are almost the same depth. Right? He's really got a full sampling. He's not just hitting a random point. And he had, I guess, 3 nights. It was a big run, right? It was basically 3 nights of data. OK, so they've understood this eclipse. So let me show that. So first off, let me just give you a sense for what are the sources of light in the system. Okay. So this big blob here is in this case, about a 0.02 solar mass helium white dwarf, for which basically they see no evidence of light. It's a 0th order. It's not an emitter. So their light sources are the white dwarf, the accreting white dwarf in blue. Okay, and they did that, I think, because it's actually the blue. It's blue compared to the other things. The accretion disk, right, which is green, and the splash point, that little spot I keep pointing out, where the stream hits the disk. Okay, and so this is their model, and these are the light curves. And so what you can see is that in the bluer channel, here's the contributions. Here's the total sum is here. Right, they've got roughly half is in the white dwarf, half is in the accretion disk. Here's the eclipse of the white dwarf. Okay, which is not complete. You can see from this image, it's not going to be a complete eclipse. Okay, this is the accretion disk, again, which is not completely eclipsed. Okay, then this is the hot spot, the fact that this spot does get completely eclipsed. Okay, so it goes out completely and comes back. Okay, and so you'll learn a lot. Okay, so I'll give you some of these. I'm excited because we'd claimed for 3 years now that the white dwarf is a big part of the light, like half. So I was happy to see that. Yeah, okay, good. Feels good. They can't deny it any longer because they've even modeled it. OK, so that's the white dwarf being eclipsed. And so what do we learn from this? Well, quite a bit. You get the inclination. There it is. So now imagine you wanted to use this as a LISA source. You've got an inclination, and you have a mass ratio that's quite accurately determined. The accretor mass and the mass of the donor, you have to do more work to get those. Okay, and they've just started. So they have this short little AstroPH, basically conference proceeding. But if it's a white dwarf that dominates, which I sort of showed the distance is probably, they don't have a distance, but this is my guess, about 250 parsecs. Okay. The donor mass for their fits is actually larger than expected. If it was completely degenerate, it would be 0.02. It's about 0.03. Okay, and so it's hot. And again, work remains. None of this has been carried out. The timing accuracy, basically, they will confirm or not that it's gravitationally wave driven within a few years, just from having very accurate timing of that center line of the eclipse. Right? So what they're going to do is use the white dwarf eclipse. So the hot spot can move around because that's the stream. You wouldn't use that. You wouldn't use the accretion disk, but you definitely could use the center of light of the white dwarf. And the fact that you've got that white dwarf in there tells you should be able to use this minimum point. It's a very good clock. And as the orbital period shifts, you'll measure it. So they showed in this paper that over their night to night, they already have a RMS accuracy in this of 1 second. Okay. And so then you can ask how long will it take you to measure the gravitational wave changing the orbital period, and that's a few years. So I think this will be an exciting system to watch.
So I didn't understand. If it's accreting, if it's transferring mass,
yes,
then the orbital period will change because of that.
Yes.
And is that a much larger or much smaller effect of gravitation?
It's all tied. They're tied together. Right. So if you tell me all this, I could go off and tell you what the P dot should be if the mass transfer is conservative. If all the mass that's being transferred is getting onto the white dwarf, I can give you a number.
And if you're uncertain about that, and if it's getting really
right. Yes.
blown away,
yes.
Then how can you disentangle that from the gravitational radiation?
You can't. I mean, they're going to get one measurement. And it either will or won't be consistent with the 0th order expectation. I mean, yeah, and I'll get into a little bit of that when I talk about these helium flashes. Thankfully, for this system of 28 minutes, I'll tell you right now, all the matter you're adding onto that white dwarf stays in terms of thermonuclear stuff. So that's good. So that's why this is another reason this is good. But there could be wind from that disk that could cause trouble. We don't see, I'll tell you, we don't see winds from these disks, though. So we'll see. Everything looks good at the beginning. You know, it's like the first date.
But let me just the comparative size of this,
Sure.
these things. So gravitational radiation goes away, energy and angular momentum is
Correct.
going to be of the same order or much larger or much smaller than some unknown wind. Some hard to measure.
Everything's tied. So the mass transfer rate is tied to the angular momentum loss rate due to gravitational waves. So if, for example, half of the mass that's transferred goes off in a wind and carries angular momentum, you'll screw up the P dot. They're all tied from the beginning.
I'm
So,
just wondering,
yeah.
we're looking for a very small effect on top of a much larger one.
You're looking for an effect that we don't know the magnitude of. I mean, if the winds are 1/100th, it won't affect it. But by 1/100th, I mean there is a characteristic mass transfer rate. Okay, there's a number. If you want to send stuff to infinity, it's relative to that number that matters. That's the right.
I just want to make sure I understand that they get the sign. What would most people get the sign?
Okay, for this case, we would all guess the sign that's moving out.
Already?
It's moving out. 28 minutes, it should be moving out. So the orbital period should be increasing. So the new dot would be negative.
I see. So these guys, the idea was they moved in, and
Yeah.
10 minutes, and now they're going back out.
They're going back out. Exactly. Right. And I'll talk about wrong sign measurements in a minute. Right? Yeah. So for this system, at 28 minutes, I think we'd all be really surprised, but we'll see. Right? Yeah. So now the work we need to do is take all these numbers and say what the value should be before it's measured. Right? Though I would claim we know enough physics that we can't fudge it. You know. The observers never believe you, though, if you do that. Okay. So I'm going to talk just briefly about this white dwarf, and then I want to sort of move through this a little bit faster than I probably should. So we got very interested in that accreting object, that little blue ball there, how it gets heated up. So that white dwarf was the first one formed, and it should be pretty cold. Okay? But you say, well, however, the accretion of material might reheat it. Okay? And so at very early times, you're accreting quite rapidly, and basically you're not heating the core of the white dwarf at all, but the fact that the matter, the helium that's on that white dwarf, is, once it gets there, being compressed and put into the white dwarf means there must be luminosity coming out. Okay? And so you can get actually a luminosity mass transfer rate relationship, which looks like this, just from the basic physics. But then remember that mass transfer is dropping like a rock. It's really high at early times, and then it drops. So basically, there's a period where the core temperature can get into some equilibrium, after which the mass transfer rate drops so fast that the white dwarf just cools. So you basically reset the white dwarf cooling clock. You sort of heat it up, and then you shut off heating, and it cools again, sort of like a characteristic white dwarf. So let me skip the theory and just see how well we did. So this bottom plot is the one to stare at. So what we're able to calculate then is what's the absolute magnitude. So this is the absolute magnitude of the white dwarf as a function of orbital period. So our theory are these lines. Okay, and there are two systems for which they actually have a parallax, so they can get an absolute brightness. And we were quite pleased that they fell at least within. You know, this is a magnet. So keep in mind, right? One reason you plot magnitudes is because any theory looks really good, right? But keep in mind, this is, 5 magnitudes is a factor of 100. Okay, so we're doing okay. These systems are puzzling, and the system I just showed you is not on this plot. It's at 28 minutes, and we don't know this yet. When I said it's at 250 parsecs, I assumed that this was the brightness. I'm assuming my theory. Okay, and that's why I think it's probably at 200 parsecs, because if this is the absolute magnitude, the apparent magnitude is 19, that puts it about 200 parsecs. Okay, so, but this is why we think that the white dwarf dominates. This is the accretion disk contribution, and this is really hard to actually have a confident understanding for. Okay, so what I want to really do, though, is talk more about this current population. So here's the current population of these systems in order of orbital period. So here's the short orbital period systems all the way down to the 65 minutes. Here's the mass transfer rate that we would expect. As I show you, as I already said, it has 6 orders of magnitude dynamic range. This is the minimum companion mass if it's a very cold object. So we go from 0.12 all the way down to 0.006, so 6 Jupiter masses. And these other things are properties of that white dwarf. Now, as I said, because of this huge dynamic range in mass transfer rate, the way they appear to us is dynamic. Let me not talk about these for a moment. These systems, the accretion disk is stable, and all the accreted matter goes onto the white dwarf at all times. And so these we actually see are pretty bright, really bright accretion disk. As you reduce the mass transfer rate, the disk goes into an unstable state where it has outbursts and then goes into quiescence. And so in quiescence, you see the helium white dwarf, the carbon-oxygen white dwarf. That system I told you about is right here, 28 minutes. So it's in quiescence, and we expect to see the white dwarf. And then some of these objects at very low state, people debate whether it's actually stable that the disk is constantly going on to the white dwarf or not. We actually don't know in these cases. So I've sort of saved you an hour of phenomenology of accretion disks. Right? But I'm not going to save you from these two systems. Okay? So these two systems were both found as X-ray sources. They have orbital, well, I'm going to presume they're orbital periods. There's a bit of a controversy, which I'm not going to share with you, because I think they're orbital periods, and you can have somebody else tell the other story. They think they're spins. 5.3 minutes and 9.5 minutes. What's special about these systems? What's special about them is that they're tight enough binaries that when you do a simple calculation of the mass transfer, you find that the accretion stream hits the white dwarf. There is no disk. Okay? And so and this was really pointed out first by Ron Webbank a long time ago, and it was worked in detail by Tom Marsh and Heiss and Danny Steegs, which is that when that material hits, you get an X-ray shock, and so some part of this star will be an X-ray emitting source. Okay? But if you're looking from this side, you shouldn't see anything from the X-rays. You might see the hot white dwarf, and indeed you do, but you don't see the accretion. Okay? Skip that. Here's what they look like. So here is the counts per second in Chandra. This is from a paper by Todd Strohmeyer, showing as a function of orbital phase, I'm going to say, what the X-ray counts look like. And he's shown two pulses here just for, they always repeat it to make you impressed by the data set. Okay, it's one set of data. Here's the line. You see it's black. It's really black in the X-rays. Okay, this is, again, such a good timing, you can actually get the change in orbital period, or the change in period of the pulse. Okay, and this is the fitting for this one object, RxJ0806, allows you to get the spin period, or the orbital period in this case is actually the period. It's moving in, so the frequency is increasing, not moving out. Okay. There's two of these systems. The other one looks just like this in the X-rays, basically the same, black, and then a pulse, and black. Okay. So we think these are direct impact systems, where the material is just directly going onto the white dwarf, and that's it. The white dwarf is constantly reheated. The material does spread around the white dwarf. We do see, if I go back to this plot, I'm not going to show you all the optical information. What do we see in the optical? We actually see light from, so this is a very hot object in the end then. The whole thing is hot and emitting, but more as a UV source. So you see evidence of this UV light. Okay? You see evidence of the heating of this companion by this bright source. Okay, and there's the phasing, so people were worried about the phasing of this. And I'm not going to show you all that, but roughly speaking, sort of this model gives you, you get the phases. This is just dynamics. This is just calculating the orbit of a trajectory, for two orbiting bodies. Okay, so there's not a lot of ambiguity for this other than the mass ratio.
The asymmetry is due to the structure of the hotspot?
Which asymmetry?
In the light curve.
Yeah, I don't think anybody can, with confidence, give you this shape. Yeah. That's how the shock, that's the emission, even if it's a point emission, right? So let me go back. Let me just say the simplest thing, right? Imagine this is really a point source, end of story, right? Then now what you're asking is, what does an observer see as they look to the side versus this, okay, for that accretion shock? And, cosine theta, you're right, it's not cosine theta, right? Because of this trailing edge. Right? But you don't see it. This is the, right? Okay. Yeah.
Second plot from the other object?
The other object.
So they both have very similar
different orbital periods. Both have new dots measured, and I'll show that now in the next plot. Okay, so this is a busy. So again, everything's going to cut off. This is new dots in hertz per second. Okay, here are the two data points. There's a data point here. This is the tight system, and here's the data point for the other. Okay, so they both have the sign of them still moving in. So this was a surprise to the community doing mass transfer, because our expectation was that once you start a mass transfer, they're moving out. They're not moving in. Okay, so sometimes prediction 1. Well, there are many predictions, but a prediction completely falsified, wrong sign. Okay. Now there's two answers to that. So Crystal Loy and Ron Tam wrote a paper pointing out that as the systems come in and as they're starting mass transfer, they are transitioning, and these systems just might be in transition. So what they're showing here is a binary coming in. So let me be clear what this is. So this is a system of a 1.025 and a 0.3 solar mass would be coming in, would fill the Roche lobe, start mass transfer, and then new dots changing sign. That's why it's going negative. Okay, for different masses. So let me tell you a few things that are clear from this. The first things that are clear is that the order of magnitude of this is entirely consistent with gravitational waves. That's the first thing to take away from this. Okay, is that these and the fact that the one that's wider orbit has a smaller new dot should make you feel good. Okay, so there are other stories about these systems, but I think this is definitely indicative of gravitational wave emission. There's sort of no doubt about it. Whether it's a direct measurement of what you'd expect from just a quad, with no funny business due to mass transfer, but the order of magnitude is clearly set by gravitational waves. Okay.
The amplitude would be what?
Oh, they're on all these plots. These are on all the standard LISA plots.
These are the LISA verification formula.
It would stand that way above confusion.
Absolutely, yeah. So I discovered an evil thing about physics today. You cannot cut and paste from their PDF files. Did you know this? You can lock PDF files, apparently. I discovered this last night.
Screen capture.
Screen capture. Yeah, I didn't figure it out. So, so there's you guys have all these plots. Somebody has them, right?
Yeah. So
these are all way above. Yeah, Kurtkin.
Lisa's best verification binary, and maybe you would have the signal to noise. Max Cook noise of the order of
Is 0806.
Is 0806.
Right. Right.
Question, the fact that we see both of these, right, in the minimal period, so that might be suspicious, because that's the fastest evolving.
Yeah. So though Crystal's my former student, I don't like this theory. Okay. I'm going to present a different solution. Okay. Okay. So last 5 minutes, I want to talk about what Heiss and I are working on right now, which is we started worrying about what happens to the helium you put on this white dwarf. Maybe it's not going to stay there. Maybe it's going to flash and be unstable. So what's shown here, again, is cut off, but this is mass of either the donor, here's the helium donor, or the mass you need to put on the white dwarf to get an explosion. Okay? So initially, you're sitting up here at very high accretion rates. Envelope's very hot. A very thin envelope mass will ignite, okay, and basically lead to an ejection of material. The donor mass is here, so you can see this contrast is about a factor of 20. Okay, well, as you move down, you evolve in time this way. You see there comes a time where there's the last big flash, after which the amount of material you need to put on the white dwarf to get an explosion is bigger than the donor. Okay? That crossover in orbital period space, well, here's the two systems I'm showing, 0806. These are the two are sitting here and here. Okay? Everything else out here is accreting at such a low rate, like that 28.3 minute eclipser. We're pretty confident that system, all the material you're putting on is just accumulating. It's too cold to do an ignition. Okay? So to us, what's interesting about these two systems is they're in this regime where this object's undergoing flashes. Okay? So there's sort of 3 points I want to make. The first point is that at early times, there'll be many of these weak flashes, and these will be helium novae. Okay? At late times, there's the last big flash, and actually this might be interesting as a faint supernovae. Okay? So we're working on that. And so let me show what happens if you do a rough model. So this is for what Heiss and I have been doing. So this is for a 1 solar mass accretor and a 0.3 solar mass donor. What he's plotting here, this is the mass you need to put on the white dwarf to get an explosion. Okay? And what he's showing is the mass building up, flashing, building up, flashing. These are the flashes. Okay? But what happens? Well, what happens, so there's roughly, again, sort of 20 flashes. Okay? Here's the last big flash for this guy, which is at a mass which is not quite a tenth of the solar mass. And I'm not going to explain this plot in the interest of time, but let me just tell you that if you have a mass that big, you can actually get a hydrodynamic runaway on the white dwarf. Okay? And that can lead to something that will probably be a faint type 1a supernovae. So we're very interested in these because if you want to find these in distant if you want to know how many of these systems are there, well, you can look in our galaxy, fine, for which you'll never see one of these flashes because it's, they're so infrequent. But what about going out and doing surveys of nearby ellipticals to look for these events, and that would allow you to constrain the population. Okay, so we're doing that side of it. What does it mean for the p dots, or the changing orbits? Well, this leads to basically a chance for a little common envelope phase in mass loss. Okay, so that weak flash definitely sends some matter to infinity. We don't know the amount of angular momentum that's lost, but we definitely would predict that after the outburst, the system's a little bit out of contact. If I send mass off to infinity, the binary widens. In which case, there's a time during which it's coming back together. Okay, and so what we would say is that that's what you're seeing, and then it's half of them should be going in, half should be going out if you're randomly through the phase. We only have 2, so that's the state of things. All right. So we think that the in-spiral phase is probably triggered by the mass loss from the last thermonuclear flash. Okay. But this is only true for the orbital periods where we can be having active flashing. And for long orbital periods, you can't have it. Okay. Okay. So what are these flash rates? So let me just ask. So if you want to, as I said, in our galaxy, you just sort of get what you get from the optical surveys. If we take that current rate, here's the birth rate of these types of binaries in our galaxy, or so we think. It's about 1 to 3 by 10 to the minus 4 per year in a 10 to the 10 L-sun galaxy. Well, we know now how many helium novae we get. We get about 20, okay, per system. So that gives us a rate in M31 of roughly this many of these events per year. So 1 every 10 years, 1 classical novae from one of these binaries in 10 years. It's about 1 in 300 observed classical novae. Okay, and then what I'm sort of calling a radioactive event, the last big flash, if every one gives me one last big flash, that ends up being probably about 1/50th of the type 1a rate. Okay, so the hope is that by measuring these or discovering these, it's a way to actually start getting at this population in distant galaxies. Now you might say, well, why hasn't it been found? Well, first thing is many of the classical novae searches use H-alpha, hydrogen emission, as a measure for classical novae. Well, I've shown you these do not have hydrogen. Okay, so that's not a good way to find them. And of course, supernovae searches are very biased against something that's got a rapid decline. So if you ask a supernovae searcher, how many systems do you see one night but not the next, there's a fair number. Okay. If you're looking for type 1a, their decay time is 15 to 30 days, so you throw these systems out. So we'll see if there's these flashes or not. Okay, so let me just stop here. You can read all this for yourself. Thank you very much.